Good morning, good afternoon, or good evening, depending upon where you are in the world. And welcome to today's webinar, Autonomous Robots, Gen AI, Vision, and Voice-Based Order Fulfillment, brought to you by Tech Online, eInfochips, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. At this time, we recommend you disable your pop-up blockers. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. If you would like to participate in our Q&A session, you can type your question at any time during this webinar into the Q&A text area and hit the submit button. If you're experiencing any technical problems, you can also type that issue into the Q&A text area, hit the submit button, and we'll be glad to offer one-on-one assistance. I would also like to encourage our attendees to complete the feedback survey that's located on the right side of your console. Please be sure to complete that before you log off today, and thank you in advance. And now, on to the presentation, Autonomous Robots, Gen AI, Vision, and Voice-Based Order Fulfillment. Discussing today's topic are Mayank Mukesh, Embedded Engineer, eInfochips. Mayank holds a Bachelor in Technology in Electrical and Electronics Engineering with honors in Power Electronics and a minor in Electric Vehicles from KIT University. He has around 2 years of experience in autonomous mobile robots, manipulators, and navigation stacks with the ROS2 framework. And joining Mayank today is Akash Parikh, Senior Embedded Engineer at eInfochips. Akash holds a Master's of Science in Mechatronics and Information Technology from the Karlsruhe Institute of Technology in Germany, with a specialization in robotics. He has around 4.5 years of diverse experience, including working with computer vision techniques, and has contributed to designing object detection, classification, and segment pipelines. It's with great pleasure I now hand things over to Mayank to begin. Mayank, take it away.
Hello everyone, I am Mayank Mukesh, an embedded software engineer at eInfochips and Arrow Company, along with my colleague Akash Parikh, senior software engineer at eInfochips and Arrow Company. We are excited to discuss autonomous robots, Gen AI, vision and voice-based order fulfillment. Looking forward to an engaging session. Here's a quick overview of what we will be covering. First, I will begin by providing introduction to eInfochips Robotics Center of Excellence and its capabilities in robotics, along with a brief introduction to robotics as well. Then we will explore the trends in robotics and different classifications of robots. After that, we will discuss mobile manipulators, how they enhance robotic capabilities in actual environments. Then we will walk through real-world demo video of pick and place through voice command. Finally, we will conclude with an open floor for your question and further discussion. This structure will guide us through the process, ensuring a clear understanding of how each component contributes to achieving the end goal. Let me begin by introducing eInfochips. eInfochips, a division of Arrow Electronics, is a key player in digital transformation and product engineering services. With a remarkable track record of developing 500 plus products deployed in 140 countries over 25 plus years, eInfochips excels in accelerating time to market. Their expertise spans across sensors, wireless, robotics, IoT, AI/ML, security, cloud, and power. Partnering with semiconductor system and software companies, eInfochips remains at the forefront of technological advancements, designing next-generation solutions for their customers. We have partnered with several customers like Qualcomm, Nvidia, ADI, NXP, etc. to deliver all aspects of the AMR solution. At eInfochips Robotics Center of Excellence, we have developed 3 versions of autonomous mobile robots equipped with SLAM and navigation technique on Qualcomm and Nvidia board. The software leverages the Nvidia robotics stack, Isaac, and robot operating system, that is ROS. We have developed the digital twin for simulation and training of the AI/ML algorithms. All our robots are cloud connected for updates. Let's begin by answering the question, what is robotics? Robotics is an interdisciplinary field combining engineering and science to design, build, operate, and utilize robots. At its core, robotics integrates multiple disciplines like mechanical, electrical, computer engineering, as well as artificial intelligence. To understand robotics better, let's break it into three core components: perception, decision making, and actuation. Perception involves sensors that allow robots to interpret data from their surroundings, like cameras, LiDAR, or IMU sensor. Decision making. Robots rely on algorithms and control systems to process the data they receive and decide what actions to take. Actuation. Actuation is about movement, using motors and mechanisms to physically interact with the environment. These components are the foundation of robotics and enable diverse applications. Think about industrial robots assembling cars, robotic arms assisting surgeons, or even robotic rovers exploring Mars. Robotics touches every field like manufacturing, healthcare, and entertainment. Robotics is a vast domain and robots come in many forms, each designed for specific purposes. Let's explore the key types. Industrial robots. These are fixed robots commonly used in manufacturing. They are precise, reliable, and perfect for repetitive tasks like welding, painting, or assembly. Mobile robots. Unlike fixed robots, these can navigate autonomously, making them ideal for tasks like warehouse management or exploration. Example includes autonomous mobile robots or AMRs. Humanoids. These robots are designed to mimic human behavior. They are often used in research, education, and some companies. Manipulators. Robotic arms are a classic example. They are specialized in handling and manipulating objects, commonly found in manufacturing lines. Hybrid systems. These combine features of different robot types. A great example is a mobile manipulator, a robot that combines mobility with manipulation. The diversity shows how robotics adapts to the unique challenges of various industries, delivering tailored solutions to complex problems. To appreciate the advancements in robotics, let's take a quick look at its evolution. In the early days, robotic systems were focused on performing repetitive and precise tasks in controlled environments. These robots, like industrial arms, were stationary and operated in fixed locations. As technology advanced, modern robotics introduced artificial intelligence and advanced sensors, making robots smarter and more adaptable. The most significant milestone in robotics was the transition from fixed system to mobile robots. Mobile robots brought flexibility, allowing robots to navigate in dynamic and unstructured environments. The big leap came when robots began combining manipulation and mobility. This capability opened up possibilities like robots working alongside humans in warehouses or assisting in disaster recovery. Now let's zoom into one of the most fascinating advancements in robotics, that is autonomous mobile robots or AMR. AMR are robots capable of navigating real-world environments without human intervention. They achieve this through a combination of advanced technologies like SLAM or simultaneous localization and mapping. This allows the robot to build a map of its surroundings and localize itself within it. Sensors. AMRs use tools like LiDAR, cameras, and depth sensors to perceive their environment. Artificial intelligence. AI enables decision making and adaptability, allowing AMR to handle dynamic situations like avoiding obstacles or rerouting when paths are blocked. Applications of AMR are incredibly diverse, including warehousing, where they handle inventory, healthcare, where they deliver medical supplies, and services industries like hospitality. AMR are the backbone of modern intelligent automation system. The next step in robotics evolution is the mobile manipulator. a robot that combines the mobility of an AMR with the dexterity of robotic arm. So what makes mobile manipulator special? They combine the best of both worlds. Mobility allows them to navigate through environments like warehouse or factories. Manipulation enables them to interact with objects, picking, placing, or even assembling components. They overcome the limitations of fixed robotic arm by functioning in dynamic and unstructured environments. For example, they can retrieve items from shelves, work alongside humans in manufacturing, or assist in medical settings. In the next phase of robotics, we will see how voice command, computer vision, and advanced robotics algorithms are driving this integration, making mobile manipulator smarter and more human friendly. Let's bring all these concepts together and explore a real world use case of advanced robotics in action. Imagine this scenario. An autonomous mobile robot is tasked with picking up a specific colored golf ball and placing it into a mug. How does this process unfold? Let's break it into steps. First, interpret the voice command. The process begins when the AMR receives a voice command. For example, someone says pick red golf ball and place it in the mug. The robot uses advanced natural language processing to understand the command, breaking it down into actionable tasks. Second, detect and localize the ball using vision and depth data. Next, the AMR activates its vision system. Cameras and depth sensors identify the ball's color, size, and precise location within the environment. This step showcases the integration of computer vision. Third, navigate autonomously to the ball. Once the ball is located, the AMR uses its SLAM system to plot a path. It navigates around obstacles and dynamically adapts to the environment, demonstrating its mobility and autonomy. Fourth, grasp and place the ball in the mug using precise manipulation. When the AMR reaches the ball, its robotic arm equipped with end effector for precise grasping picks up the ball. Then with careful coordination, it places the ball into the mug. Outcome. This seamless sequence highlights the synergy between voice recognition, vision, mobility, and manipulation. It demonstrates how advanced robotics can achieve complex tasks with minimal human intervention, delivering efficiency and adaptability in real-world scenarios. This slide outlines the roadmap for our discussion. Here what we will cover step by step. Customized robot design in Fusion 360. We will start by exploring how the robot is customized and designed in Fusion 360 to suit the specific requirement of our use case. Flow diagram, first iteration. We will introduce the first iteration of the workflow, breaking it down into distinct components like speech to text, how the robot interprets voice commands, LSTM, how the system processes sequential data for better context understanding, YOLO, an overview of object detection using the You Only Look Once algorithm, object tracking algorithm, the method for tracking objects in dynamic environments, Megapose 6D or 6D pose algorithm. It is a step to accurately determine the object's position and orientation in 3D space. After discussing the workflow, we will move on to a practical demonstration to showcase how all these components come together. Next, we will revisit the workflow and look at potential improvements or refinements for a more efficient implementation. Let's take a deeper look at three key components in the workflow that make the system work seamlessly. Speech to text. The first step is converting the voice commands into text. This component enables intuitive interaction between humans and the robot, breaking language barriers and making communication natural. We use advanced speech recognition algorithm to ensure accuracy, even with varied accent or noisy environments. LSTM, long-term memory. Once the voice command is converted to text, it's processed by an LSTM model. LSTM are a type of neural network designed to handle sequential data. They excel at remembering context, which is vital for understanding commands like pick up the red ball next to the blue mug. This ensures that the robot interprets command accurately, even when there are dependencies between words. YOLO, you only look once. After understanding the command, the robot uses YOLO for object detection. YOLO is a cutting-edge algorithm that identifies objects in real time. It's highly efficient and can locate and label objects with exceptional speed and precision. For example, it helps the robot identify the red ball among various objects in its field of vision. These three components work together to ensure the system understands the user intent, processes it efficiently, and locates the desired objects in real time. So, what is forward kinematics? It's the process of calculating where the end effector of a robot is based on the known angles or position of the robot's joints. For example, if you input how much each joint has rotated, forward kinematics will compute the exact position and orientation of the gripper or tool in 3D space. So how does it work? Forward kinematics relies on mathematical models, specifically transformation matrices, that define the relationship between each joint and the next. By chaining these transformations together, we can calculate the end effector pose. So why is it important? First, position verification. It ensures the robot's end effector reaches the correct location during tasks. Path planning and simulation. It helps predict and visualize the robot's movements in software before executing them physically. In our robot, forward kinematics allows us to compute the gripper location precisely when we know the joint configurations. This is critical for basic operations like positioning the arm for a pick and place tasks. While forward kinematics tells us where the end effector is, the next step, inverse kinematics, help us figure out how to reach a desired position, which we will discuss in coming slide. Now that we understand forward kinematics, let's move to its counterpart, that is inverse kinematics. Inverse kinematics is the process of determining what joint angles or position are needed to place the robot's end effector at a specific target position and orientation in space. So how does it work? Unlike forward kinematics, where we calculate the end effector position from joint angles, here the input is the desired position of the end effector, and the output is the required joint configurations. Solving this is often more complex because there are multiple solutions or sometimes no solution depending on the target. So why is it important? Precision manipulation. It allows the robot to reach specific targets even in unstructured environments. Motion planning. In tasks like picking an object or assembling a component, inverse kinematics ensures the robot's arm moves smoothly and accurately to the required position. For example, if we want our robot to pick up a mug placed on a table, inverse kinematics calculates the joint angles required to position the gripper precisely over the mug. Together, forward and inverse kinematics form the foundation for robotic motion and manipulation, enabling robots to interact with their environment effectively. Let's move towards ROS2. We are using ROS in our robot. The Robot Operating System ROS is a set of software libraries and tools for building robot applications. It acts like middleware on top of the operating system. It has publisher and subscriber mechanism for data transfer. ROS2 uses DDS, Data Distribution Services, as its middleware to handle communication between components. It works on Linux, Windows, Mac OS, and RTOS. The architecture of ROS2 follows a modular approach. At the core, it has nodes, which are individual components of a robotic system. These nodes communicate using topic for continuous data streaming. and services for request response interactions. ROS 2 brings several major improvements over ROS 1. The real-time capability allows robots to react faster, making it ideal for applications like self-driving car or industrial automation. ROS 2 also eliminates the need for a central ROS master by using DDS-based communication, making it more reliable and scalable. Security has also been improved in ROS 2 with encryption and authentication, making ROS 2 safer for commercial applications. The future of ROS 2 is exciting. Developers are integrating AI and machine learning, allowing robots to learn and adapt to their environment. Cloud robotics will enable robots to access powerful computing resources remotely, improving efficiency. As adoption increases, ROS 2 will likely become the industry standard for robotics, with ongoing improvement in usability, real-time performance, and AI integration. Now we will see about nav2 for navigation. For autonomous navigation, we are using nav2 in our robotic software stack. nav2 is the official navigation framework for ROS 2. It allows robots to move autonomously with avoiding obstacles and reaching their goals with good accuracy. Not only with nav2 robot move from point A to point B, but it can have intermediary poses and represent other types of tasks like object following, complete coverage navigation, and more. nav2 is a production grade and high quality navigation framework trusted by lot of companies and researchers worldwide. It provides perception, planning, control, localization, visualization, and much more to build high reliable autonomous system. nav2 operates using different modular components including planner server, controller server, BT navigator, cost map server, and recovery server. Planner server computes the best path. Controller server ensures smooth movement of robot. BT navigator uses behavior tree for smart decision making. Cost map server create a real-time map for obstacle detection. Recovery server help the robot recover from failure. By working together, these components allow robots to move efficiently and handle unexpected situations. To summarize, nav2 is a production-grade navigation framework that provides everything needed for autonomous robot movement. It is used in warehouses, hospitals, homes, and even outdoor exploration. With its advanced behavior trees, modular design, and real-time processing, nav2 is shaping the future of robot navigation. Now my colleague Akash Parik will explain remaining slides. Over to you, Akash.
Now let us move to the CAD model of this robot that I created in Fusion 360. This model was not just a static design, but also played a crucial role in testing and validation. The design includes a sturdy and compact base optimized for hosting various components like motors, sensors, and the manipulator arm. You can see placement for key sensors such as the camera and LiDAR, which are vital for the robot's navigation and object detection capabilities. What makes this model special is that it was used in Gazebo for simulation testing. Before building the physical robot, I ran simulations of algorithms like navigation, path planning, and object manipulation using this virtual model. These tests allowed me to identify and address any potential issue in the robot's design or algorithms without incurring the cost of physical trials. Once the algorithms performed as expected, they were transferred to the physical robot for real-world validation. This CAD model bridged the conceptual and practical stages of development, ensuring the robot's functionality before assembly. Here's a glimpse of the actual robot that we built based on the design in Fusion 360. If you compare this with the CAD design, you will notice that we stayed true to the blueprint. Every detail, from the frame to the maneuver arm, has been meticulously recreated to ensure the robot performs as expected in real-world scenarios. This transition from design to reality highlights the importance of accurate modeling. Fusion 360 allowed us to visualize the entire system before fabrication, and this is the result. Now that you have seen the finished robot, let's break it down further and take a closer look at its component in the next slide. Let's dive into the core components that make up this robot. On this slide, you can see an image that highlights the key parts. Here's an overview of each component. First of all, controller board. This is the brain of the robot. It processes all the input from sensors and executes the commands for navigation and manipulation. Second one is motors. We have used two high torque motors for movement. These provide the necessary power and precision for the robot to navigate dynamically. Third one is manipulator arm. This arm is equipped for object interaction, designed specifically for tasks like picking and placing. Fourth one is camera. The camera is a crucial part of robot's perception system. It enables object detection and recognition using algorithms like YOLO. Fifth one is lidar sensor. The lidar ensures the robot can map its surrounding and navigate autonomously, avoiding obstacles while reaching its target. Sixth one is battery. The battery powers the entire system. It's chosen to provide a balance between performance and runtime, allowing the robot to operate for extended periods. Each of these components plays a critical role in the overall functionality of the robot. Together, they enable it to perceive the environment, make decisions, and execute tasks effectively. Understanding the hardware is essential because it sets the foundation for integrating the software, which is what brings this robot to life. Let's now transition to the software side, starting with the flow diagram of our algorithm. This diagram represents the complete operational pipeline of the robot, broken into distinct modules. It starts with a voice command, where the user communicates their intent through spoken instructions. This input undergoes speech-to-text processing, converting it into a textual format, which is then interpreted by an LSTM-based model. The LSTM classifies the input into a specific command category, represented as a class ID. Based on the identified class ID, the pipeline initiates the object tracking module, where the robot actively searches for an object of interest within its environment. The system continuously evaluates a stopping condition, a predefined criterion that determines whether the aimer has been reached to a specific location. If the stopping condition is met, the robot transitions to the 60 pulse pipeline, where it calculates the object's exact location and orientation in three-dimensional space. This enables precise control of the robotic manipulator arm, powered by the Move-It-To framework. The system concludes by executing the final task, such as picking up a golf ball and navigating the robot back to its home position. The pipeline begins with the user's voice input, which serves as the primary interface for communication with the robot. The spoken words are captured through a microphone, initiating the process. First, the audio is converted from analog to digital form, enabling it to be processed computationally. The system uses an acoustic model to analyze and identify phonemes, which are the fundamental sound unit of speech. Next, a language model comes into play, which evaluates grammar, word probabilities, and context, ensuring the decoded text aligns with natural language patterns. Finally, a decoder algorithm selects the most likely sequence of words to represent the spoken command accurately. This output is then passed on to the next stage in the pipeline for further processing. After the voice command is converted to text, the LSTM-based model processes the data. This model is particularly well suited for handling sequential information like language due to its ability to understand temporal patterns. The input text is fed into the LSTM one word at a time, enabling the model to identify patterns and relationships across the sequence. By doing so, the LSTM effectively extracts meaningful insights and classifies the command into one of the predefined task categories, generating unique class ID. The model's strength lies in its capacity to handle complex sentence structures, ensuring accurate understanding of user intent, even in scenarios where language nuance might arise. Once the LSTM generates a class ID, indicating the need for object tracking, the pipeline activates the object tracking module. This begins with object detection using the YOLO V8 model, which identifies the object of interest within the robot's field of vision and generates a bounding box around it. The bounding box data is then passed to an object tracking algorithm, which continuously monitors the object's position. This enables the robot to follow the object dynamically as it moves. For navigation tasks, the pipeline integrates with Nav2, which replaces tracking by commanding the robot to approach the object. This stage ensures the robot remains focused on its target, providing the precision required for seamless task execution. When the object tracking module determines that the stopping condition has been met, which is indicating that the object is in the desired position, the pipeline transitions to the 6D pose calculation stage. Here, the system activates the Megapose algorithm, which uses depth and RGB image data to compute the exact position and orientation of the object in 3D space. This critical information is then fed into the MOVEit2 framework, which generates precise control commands for the manipulator arm. With this data, the arm performs the required tasks, such as picking up a golf ball. The 6D pose pipeline ensures that every movement is executed with accuracy and reliability, bringing the pipeline closer to the task completion. Now let's talk about MOVEit2. It is a very useful tool in robotics for motion planning and manipulation. MOVEit2 is an open source framework that provides powerful capabilities for motion planning, control, and manipulation of robotic systems. It builds on the success of the original MOVEit framework, but it is now fully compatible with ROS2, making it even more robust and efficient for modern robotics applications. Some of the key features of MOVEit2 are as follows. First, motion planning. MOVEit2 generates optimal path for robotic applications, ensuring smooth and efficient movements. Second, collision avoidance. The framework constantly monitors the environment to ensure the robot avoids obstacles. Third, kinematics. It handles both forward and inward kinematics, which are crucial for precise manipulation tasks. Lastly, integration. MOVEit2 seamlessly integrates with ROS2, giving it enhanced real-time capabilities and making it adaptable for different robotics applications. So now the question might arise that why do we use MOVEit2? That's because it is a flexible and modular framework that supports real-time applications, making it ideal for tasks ranging from research to industrial use cases. For example, in our robot, move to handles the planning and control of motor arm. Whether it's picking up object or placing them, move it to ensure smooth and precise movements. Let's take a look at the system in action. Here we have our setup, an AMR equipped with a robotic arm. The golf ball is placed at a distance, requiring the AMR to move towards it before picking it up. On the screen, you can see the camera feed on the right side. Once we give the command, the object detection algorithm kicks in, identifying the golf ball with a bounding box. Now the AMR begins its movement, navigating towards the ball using the real-time tracking. It is ensuring that it precisely reaches the correct position. Once in position, the robotic arm executes the pickup using forward kinematics. With the ball secured, the system now shifts focus to the next objective, locating the mug. The AMR begins scanning for it, continuously updating its path based on real-time visual input. You will see, as someone moves the mug, the AMR dynamically adjusts its position. This demonstrates the adaptability of the system. It's not just following a pre-programmed path, but actively responding to changes in the environment. Finally, the AMR reaches the mug and carefully places the ball inside, completing the entire process seamlessly. From detection to navigation, pickup, and placement, this showcases full capability of our system. This demo highlights how AI-driven perception and control allow the robot to interact dynamically with its surroundings. This demo is similar to the one we just saw in previous slide with one key difference. On the right, you can see a 2D map representing the environment. When we give a voice command, Nav2 generates a path on the map showing the planned route for the AMR to reach the golf ball. As the AMR follows this path and reaches a predefined threshold distance, the object tracking algorithm takes over, ensuring precise positioning for an efficient ball pickup by the robotic arm. After successfully picking up the ball, the system searches for the mug just like in the previous demo. Again, Nav2 computes a path towards the mug location. Once the AMR gets close enough, crossing another threshold, object tracking takes control to ensure accurate placement of the ball into the mug. Now, let me walk you through some of the key challenges we faced during the development process and how we overcome them. First, using inverse kinematics to control the arm. Our robotic arm is designed with 4 degrees of freedom, but applying inverse kinematics effectively requires 6 degrees of freedom. To address this, we constrain the arm's movement in one direction, allowing us to achieve the desired control and functionality without redesigning the hardware. Second, compensating for navigation errors caused by sensor inaccuracies. These errors could prevent the robot from reliably reaching the target location. To resolve this, we developed a robust object tracking algorithm that dynamically adjusts for errors, enabling accurate navigation even under challenging conditions. Finally, time constraint when implementing the 60 pose algorithm. After reaching near the ball, the 60 pose algorithm was taking too much time to determine the precise location and orientation of the golf ball. Since it processes 3D data to compute the exact relative position, this step required significant computational effort. To address this, we further refined the object tracking algorithm, ensuring the AMR could consistently reach the precise location where the ball is located. By integrating forward kinematics with robust tracking, we ensured the arm could consistently perform its task with greater efficiency and reduce execution time. These challenges pushed us to innovate, and the solutions we implemented significantly improved the system's accuracy, reliability, and efficiency. In our second approach, we introduced two major improvements: NVIDIA Riva for speech-to-text and NanoOwl for object detection. Instead of relying on cloud-based APIs, this approach ensures low latency processing and enhances system reliability. Once the voice command is processed, we send the text to a GenAI model, which determines the object we need to locate. Unlike traditional object detection models, we opted for NanoOwl, which excels in zero-shot detection. This means the system doesn't need prior training on specific objects. It can recognize and track new objects simply from description. This flexibility is incredibly useful in dynamic environments where predefined object dataset may not always be sufficient. With the detected object, we generate a bounding box, which is then fed into our object tracking module. The tracking ensures smooth execution even if the object moves. Once the stopping condition is met, the move it to motion planning framework takes over, guiding the robotic arm to precisely execute the task. What makes this approach powerful is its adaptability and efficiency. By eliminating the dependency on pre-trained detection model and cloud-based speech recognition, we have built a system that is faster, more flexible, and capable of handling real-world variability. Ultimately, this approach pushes us closer to real-time intelligent robotics interaction, where commands can be processed instantly and objects can be manipulated dynamically, making the system more autonomous, responsive, and scalable. Now, let's take a look at NVIDIA Riva and why we chose it for our speech recognition pipeline. In our first approach, we used a traditional speech-to-text API. While it worked, it had limitations, mainly latency and cloud dependency. We needed a solution that could work in real time on the robot itself, without depending on internet connectivity. This is where NVIDIA Riva comes in. Riva is an on-device speech recognition framework optimized for NVIDIA GPUs, including Jetson Xavier and Orin. It allows us to process voice commands with extremely low latency, ensuring that the AMR can interpret and act on commands instantly. Another key aspect is its Edge AI capabilities. Since Riva runs entirely on the robot's hardware, there is no need for an internet connection, making it a secure, efficient, and scalable solution for robotics. By integrating NVIDIA Riva, we achieved faster, more reliable speech recognition, improving the overall efficiency and responsiveness of our AMR systems. It plays a crucial role in ensuring that voice commands are accurately processed, allowing for seamless interaction between the user and the robot. The second thing we changed in this approach is object detection model, which is NanoOwl. Unlike YOLO, which is a powerful but computationally demanding model, NanoOwl is specifically designed for edge devices. This means it runs efficiently on platforms like Nano, making it ideal for real-time robotics applications where low latency is critical. One of the biggest advantages of NanoOwl is its ability to deliver fast and accurate object detection while using less computational power. This efficiency ensures that our system remains responsive without requiring high-end GPUs or cloud-based processing. This is particularly important for our autonomous system, where decision-making must happen in real time without delays. Another critical aspect is its small model size. Unlike larger object detection models that require extensive memory and processing power, NanoOwl remains lightweight while still maintaining high accuracy. This makes it an excellent choice for embedded AI applications where hardware constraints are a key consideration. By integrating NanoOwl in our pipeline, we were able to achieve seamless and efficient object detection. It played a key role in ensuring the AMR could quickly and accurately detect objects in its environment, making the overall system more robust and responsive. In summary, by switching to NanoOwl, we significantly optimized our workflow, reduced processing time, and made the system more scalable and deployable for real-world applications. To wrap up, let me summarize what we have accomplished with this project. First, we tackled significant technical challenges to develop a robust and efficient system capable of executing the ball pickup task with high precision. By leveraging advanced algorithms such as inverse kinematics, 60-bus estimation, and object tracking, we overcome key obstacles in navigation, control, and accuracy. Each component was carefully optimized to ensure smooth coordination between precision, motion planning, and execution. However, this project isn't just about solving a single task. It represents innovation in robotics and highlights its real-world impact. It showcases how autonomous systems can be applied to practical problems, enhancing automation in various industries. More importantly, it serves as a foundation for even more complex and adaptable robotic solutions. Looking ahead, there is immense potential to expand this work. By integrating machine learning, the system could dynamically adapt to new scenarios, improving its decision-making capabilities. Additionally, scaling it to handle different types of objects in different environments could make it suitable for applications beyond this specific use case, such as warehouse automation and assistive robotics. Ultimately, this project is both a technical milestone and a step forward towards the future intelligent automation. It reinforces the power of robotics in transforming everyday tasks and paves the way for even more advanced applications. Thank you.
Well, thank you, gentlemen, for an excellent presentation. To our audience, we are now moving on to the question and answer portion of the event. If you haven't done so already, please go ahead and enter your question now into the Q&A text area. Please note that we'll get to as many questions as we can in the time we have left. So, gentlemen, I hope you're ready. We've got several questions coming in here. First one asks, why did you switch from the first approach to the second approach?
Yeah, I will take that. So as I mentioned in the presentation, that the second approach using NVIDIA Riva and NanoOwl, it provided better performance and flexibility. So we can, directly, by consuming less time, we can detect object. That's why we chose the approach.
Excellent. Thank you, sir. Moving on to our next question. How does object tracking contribute to the system's accuracy?
Yeah, hi, I am Mayank. I will take this question. So, it continuously monitors the target position and ensure the precise localization of AMR. That's why the object tracking contributes to the system accuracy in navigation as well. So, yeah.
Excellent. Thank you, sir. Next question asks, how does the AMR handle dynamic obstacles during navigation?
So the AMR uses NAV2 for path planning, which is dynamically adjusts its path when obstacles are detected. So this is how how obstacles it handles obstacles during navigation.
Very good. All right, quickly moving on here to our audience again. If you've got a question, go ahead and enter that in. We're going to get to a few more here, but someone will get back to you after the program. Next question asks, can this system be adapted for different objects and tasks?
Yeah, hi. So I am Mayank. I would like to take this question. So to adapt for different object and tasks. So yes, with training and minor adjustments, this system can handle various objects and even more complex tasks. So yeah, we can adapt this for more complex tasks as well.
Excellent. Thank you, Mayank. Looks like we've got one more question here, and it says, why do you choose Nano Owl over YOLO version 8 for object detection?
So we chose that because Nano Owl offered lightweight architecture with faster inference times, making it ideal for real-time applications on our AMR. So basically, it will reduce our time, and that's why it is better. Or it will also take less computation time. That's why we chose that.
Excellent. Thank you very much. So thank you both, gentlemen, for a great Q&A and presentation, of course. And for more information related to today's webinar, please visit any of the resource links located in the green folder icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. And if you have not filled out that feedback form, please go ahead and complete that. So thank you for attending today's webinar, Autonomous Robots, Gen AI, Vision, and Voice-Based Order Fulfillment, brought to you by Tech Online, eInfoChips. This webinar is copyright 2025 by AspenCore. Presentation materials are owned by or copyright by Tech Online and eInfoChips, and the individual speakers are solely responsible for their content and opinion. On behalf of our guests, eInfoChips, I'm Colleen Heckman. Thank you for your time, and we hope you have a great day.